Yeah. All right. Hi guys. Thanks for coming. Today I'm going to be talking about the FRI protocol. This is like fast Reed-Solomon interactive Oracle proofs of proximity. That's a mouthful. We'll get to what all those things mean in a bit. Before we start, I want to like really clearly lay out what my goals are and also give some credit. A lot of this slide content is pretty much stolen directly from Professor Chiesa and in his course. I really wanted to be original and I thought a lot about it, but there's this saying that a couple of my previous mentors had told me, which is kind of a joke, but true in spirit, which is that if there's a God out there, he keeps a book by his side of all of the best proofs possible that really, really show you the intuition of how to get from A to B. And I do believe that like Professor Chiesa's presentation of the FRI protocol is something that is as close to that book of God that humans can possibly come to. So with that said, that's a lot of high praise, but I mean it. I did not see like enough motivation to actually deviate from the way that he's taught it. So I'll put my own unique spin on things and please ask questions, of course. My goal here is to really teach intuition rather than every single detail behind the FRI protocol, because we would be here for hours and hours if I tried to do that. Now, if there's one thing that you guys should have taken away from this course when it comes to life, it's that interaction is very, very powerful as a tool to learn more complicated things. So what I request is that like this is going to be a technical talk. I'm going to do my best to not introduce any like complicated math that's unnecessary, but at the same time, it's going to require focus and it's going to require you guys to really dig in, to really grok and understand this material. So what I'm going to say is I'm going to err on the side of going a little bit slower than usual, but it's still going to be quite fast. So what I request is that if anybody at any point is confused about something, please do not be shy to interrupt me and ask any question. Yeah, that helps me, honestly. Like if you don't want to, like, if you feel bad about it, just think about it. You're helping me because, you know, I get to make sure that I really understand the topic too when I'm teaching it. So yeah, that's just my little pre-lecture spiel. I just want to set expectations for what's about to come. Yeah, so here's a lesson plan that we're going to like vaguely follow. We're going to talk about the background and motivation for the protocol. We're going to go through the protocol construction. We're going to talk about the soundness of FRI, which is actually quite non-trivial. And then we're going to talk a little about, if time permitting, about like extensions and further work. Cool. So without further ado, let's start with the motivation. If anybody is watching this recording and they weren't in previous classes or they're like not even in this class, this motivation is going to be very tailored to what we've been doing in the class so far.
Is there a way to make this bigger?
I don't know.
I can try. If not, it's fine. I'm just wondering.
Yeah, sorry.
It's kind of small.
Is this legible? Kind of.
Yeah, that's
okay.
Good.
Cool. I'll keep this size. For those who are not in the class, yeah, this motivation is going to be very like specific to what we've been learning in this class. So it's going to be motivation as pertaining to information theoretic proof systems. However, after that, like the background, etc., that's all just FRI stuff. So if you care about that, feel free to skip to that part of the lecture. Anyways, so let's motivate why we care about FRI. So far, we've discussed various PCP constructions for NP. We've talked about some exponential sized PCPs. And here we use like linear extensions, or another way to talk about that is like a Hadamard code. And we use this to prove that like, well, we didn't actually show this. Maybe we did. That NP is a subset of PCP poly. And here this means like, you know, how many bits of randomness. And here this means like the number of queries that the PCP verifier is doing. And one of the ways you can do this is you can start with a linear PCP of poly size, and then you can compile it into a PCP. And the way this would work is the PCP prover would write down pretty much every query answer to the linear PCP. The PCP verifier would read the query answers and then just run the LPCP verifier. And then there's one extra step which introduces a little bit of a soundness degradation, which is that the PCP verifier would run a linearity test on the prover's PCP strings, the query answers. Right? There's a new vector for how the PCP prover can cheat. They can make sure that their query answer. They can not make their query answers actually a linear functions evaluations. In that case, we can't rely on the bootstrapping of our LPCP soundness result. So this was a crucial step here, right? This this compilation from LPCP to PCP required this linearity test. Cool. For poly-sized PCPs, we use these multivariate low-degree extensions. Another way to talk about that are Reed-Muller codes. Just a quick recap of how we did that. We chose some NP-complete language. In this case, it was quadratic equations. And then the prover low-degree extends some assignment vector W into this W hat, let's call it, right? And W hat is now a multivariate polynomial. And then the verifier runs some check to test that this W hat satisfies the quadratic equation instance. And finally, there's this one extra step that I've highlighted here. The verifier runs a low degree test to ensure that W hat is well formed. Specifically that there actually is some binding assignment vector underneath this W, and that some other notion of well formed related to the quadratic terms, which I'll defer to previous lectures if you want to look at those details. So now finally, we want to talk about what about linear sized PCPs for NP? We had these poly-sized PCPs for NP. Well, what do I mean by linear? I mean linear in the instance of the witness. But NP reductions don't necessarily need to have a linear blowup. They're allowed to have a polynomial size blowup. So the best that we could really hope for is linear-sized PCPs for some NP complete language at best. That's not going to give us linear-sized PCPs for every NP language. Fair. So let's pick an NP complete language.
So there's works on having quasi-linear-sized PCPs. So given a proof, they get transformed in one which is a quasi-linear size in the original proof. What's different here?
Oh, interesting. I didn't know that there was a way to do quasi-linear.
Absolutely. This is a classic work by Sudan and Ben Sasson,
cool.
From many years ago. This is quasi-linear size PCP, right? So I don't know what. It would be different if it was. That's quasi-linear in the proof. Maybe now you want to be quasi-linear just in X. That would be new.
Right. Sorry, I just got a notification the Zoom meeting is about to expire, so I'm extending it really quickly. But would you mind sending me that paper? I'm quite interested in that. I'm not very familiar with this topic either.
So this is a linear size PCP. Right?
Yeah, this is a little bit better.
Even smaller.
So maybe that's the issue. You really want linear, not quasi-linear.
Yes, that is true.
That's completely different. Quasi-linear, that's I will not give you linear. So you really want linear, yeah. That's what you're aiming for.
Yeah, exactly.
Okay.
Give me 2 seconds. I need to upgrade to Zoom Premium, and then I'll be able to continue with this lecture. I just assumed that you would have given us Zoom Premium already. Apologies, guys. Okay, this meeting now has unlimited minutes. Great. Sorry about that. Cool. Yeah. So linear size PCPs. Yeah, even better than quasi-linear. Now, yeah, like I said, we can't really hope for a linear size PCP for every NP language, but we can hope for some NP complete language, let's say. So the example that we'll take here is R1CS, which is a relaxation of quadratic equations, but still NP complete. Now, a slight detour. We're going to talk about.
We could also hope for linear size PCP for every.
We could, but that's definitely a harder thing to do. Let's say.
Yeah. So you're doing it just for a problem. Okay.
Yeah. You're absolutely right. Let me re-clarify what I was trying to say. We can't just show a linear size PCP for one NP complete language and then say that we have it for all of NP.
Right.
That's what I really meant to say. Yeah, thanks. Cool. So let's make a slight detour and let's talk about IOPs. So IOPs are basically a generalization of PCPs to multiple rounds. They're still an information theoretic protocol between a prover and a verifier. And basically, I think the picture speaks 1,000 words here. Like the prover can send a proof string, the verifier can send a message, proof, message, etc. And it turns out that like adding these new rounds like really does give you like more than you'd expect it would. Like this is a more powerful paradigm, well, assuming some like complexity theory results that are unknown, than this. I'm not going to go on a complexity theory deep dive because I'm just frankly not qualified to do so.
So here the verifier just reads like a constant number of bits from each message?
Yes, yeah. So, well,
Okay.
yeah, I mean, you say the query complexity of the verifier here is like, you know, how many bits it read in all of these. Maybe like one slightly subtle notion, which is not important for today's talk, but just generally, is that like after you send pi2, the verifier is allowed to read pi1 and pi2 anywhere it wants. It doesn't just have to read one.
Fine.
It's not super important for today, but generally, if you're looking at IOPs, that's something neat to know. So we'll define the size of an IOP proof as like, you know, the size of all of the prover messages were ever sent. Okay, and then we have this theorem, which like is really not the point of today's talk, but it's just to motivate today's talk, is that we have a linear sized IOP protocol for R1CS. And the key ingredients are we do like univariate, not multivariate, univariate low degree extensions of some witness vector. And then we will do an IOP for univariate sum check, and this turns out to be linear in size. And then finally, we'll also do like an IOP for univariate low degree testing. And this is really what we're going to be talking about today, right? Like, so jumping ahead, basically we're trying to get like a IOP to test proximity to a Reed-Solomon code. And that's basically the same thing as like an IOP for univariate low degree testing. Cool. So with that said, that's the motivation section done and dusted.
Was it R1CS? Are you going to define it? I missed the last one.
No, I'm not going to define it. It's not like super important to the talk. The only thing I wanted to really say about it is that like it's some NP complete language. These are the ingredients. It kind of looks like the ingredients that we had earlier for poly-size and exponential size PCBs. And like the one of the key things that you need to do is like some low degree test or some linearity tests.
But basically the message that I'm getting is that somehow if you allow for interaction, actually the low degree tests are easier to do.
Yes, this is true. Yeah, that's actually a great point. So there are like proximity tests for Reed-Solomon codes that are like you know, not that aren't interactive. Let's actually think about that for a second, right? Like I this might be getting ahead of myself, so if this doesn't make sense to some people, that's fine, but I'll just like say it 1 or 2 sentences about this. If you have a degree D polynomial, right? You have the claimed evaluations of a degree D polynomial, right? You would need to read at least D+2 points before you could ever have any information about the fact that like, hey, this was not really a degree D polynomial. Because if I read any D+1 points as like a non-interactive verifier, if I query any D+1 evaluations, that could have corresponded to some degree D polynomial. So in the case where like the degree is large and we don't want to allow for like the degree number of queries, we should do something that requires like the prover's help, some interaction. Okay. That actually wasn't like a very formal proof, but it's just some intuition. Okay, let's get into the background. There's some linear algebra. I'm gonna try and keep it as short as possible. If I'm boring everybody, please tell me to just like go faster. I don't know what to assume and what to not assume.
Can I ask a question?
Yeah, sure.
Maybe I just missed something, but can you motivate why now we're using the IOP for proximity testing? Like, and maybe I just missed something.
So basically, like, I'll kind of refer you back to this because maybe you're more familiar with this like poly-sized PCPs for quadratic equations, right? We like have this thing here, W hat, which is like in this case, like a multivariate polynomial, right? And we run a sum check on this multivariate polynomial to check the quadratic equation instance. But how do we know that this multivariate polynomial like is really like binded to some actual assignment vector? That's where we use the low degree test. So similarly, like here,
Yeah,
Right.
for all right, yeah, for the R1CS theorem thing.
yeah. What was the question?
Like I guess where the text turned blue.
This
This
one?
jumping ahead thing, yeah.
Oh, jumping ahead. Oh yeah, this
Like,
is
if-
this really is jumping ahead. I will explain like why.
Okay.
Like what Reed-Solomon even is. I haven't even defined that, for instance.
Sure. Okay.
Sorry. No worries. So let's go to the background. Let's talk about a little bit of linear algebra. Hopefully, like the minimal amount possible, but we'll see. So definition: a linear code over some like field f. For now, we can assume that f is some finite field. It's a subspace of f to the n, where you can think about f to the n as being like an n-dimensional vector space over f. Okay, so we say that like C subset, a subspace of f to the n, is like our code of dimension k. You have like a subspace of dimension k, it has k basis vectors. That means that there's like this encoding map, right, from f to the k to f to the n. And basically I take like these k message like scalars, and I can turn it into this code word. Okay, and specifically like this encoding map, is injective, and the image of this encoding map is exactly our code C, our subspace. Okay. So why am I presenting it like this? Some notes, right? Like 0 is always in your linear code. And then, you should be able to do the normal things you're able to do in vector spaces. So notably, like the difference between two code words is also going to be a code in any linear code. Okay, I'm going to now define the Hamming distance function. And this is just a function which takes in two words in what I'll call the ambient space, f to the n. And it just measures how many components of x and y are different. This is a perfectly good metric, and it obeys triangle inequality, for instance. Now, the distance of a linear code is just like the minimum distance between any two code words. Happens to be equivalent to just like the minimum weight code word too, and I'll leave that as an exercise because of linearity of this code. But yes, the distance of a code is this. I have abused notation here slightly later in the talk where there's this thing called distance. There's also this thing called relative distance, which is basically where I normalize this value, and I basically like divide this whole thing by n. I think it should be clear from context when I'm talking about distance and when I'm talking about relative distance. But yeah, just a warning ahead. Okay, finally, now I can talk about a specific type of linear codes called Reed-Solomon codes, right? And the way this works is like we fix some natural number n, and then we fix some domain of like n points in like our field. And now what I'll do is I'll define a Reed-Solomon code of message length k and block length n. Again, that's like n is like the dimension of the ambient space, and k is like the dimension of my subspace or the code. And I can say that like C is the Reed-Solomon code defined like this, which is basically like the vector of evaluations of these endpoints of some degree less than k polynomial. If anyone hasn't seen this before and is like totally lost, please stop me. But otherwise, I'm going to assume that maybe this is review. But if someone hasn't seen this before, please stop me before I like shoot off at lightning speed.
You have two messages in the chat.
Oh, I didn't even see. Oh no, those are previous messages. I'm logged into Zoom from 3 accounts. Cool. Okay. Yeah. So one fact about Reed-Solomon codes is that like if I look at any two code words. I'll just say the thing. These things are called like maximum distance separable, which just means that like it's a really good packing scheme if you think about this geometrically. What I'm trying to say is basically this: like if I encode two code words, right, like some polynomial and some other polynomial, so I can look at its like coefficients and encode them, right? Then I claim that the distance between those things must be at least n minus k plus 1. And this basically just stems from your favorite like algebra theorem, which is that like two distinct polynomials of degree at most k minus 1 can agree on at most k minus 1 places. So the minimum distance of our like Reed-Solomon code is n minus k plus 1. As a fact, Reed-Solomon codes are linear codes. We can define the rate of a code to be like, you know, basically how much redundancy this code has. So like, you know, how many, the dimension of the code over the dimension of the ambient space. If I have higher rate, if rate is like 1, that means there's basically no redundancy. If rate is like really low, that means that I'm, you know, huge blow up from how big a message is to how big a code word is, but there's lots of redundancy. And then finally, like, I know I'm just like going into so many definitions, but they're going to be all necessary, unfortunately, is that the distance of a word to a code is just like, you know, the minimum distance of that word to any code word. Okay. Final comment I want to make in this background section is that we can think of any word in f to the n as like a function from L to F, right? Like there's sort of like this one-to-one correspondence of like thinking about, you know, a vector of evaluations and like a function that maps like some domain to some like a field element, right? Like you can sort of think about indexing each of these things in the vector with some like element in the domain. Hopefully that's clear. Cool. Yeah, that's the background. Does anyone have any questions? If not, we can get into the good stuff.
Do you think if you change the view, have the images, I mean, like the video
Yeah,
on
I'm gonna
the
try that.
side?
Let's see. Let's see how well this works. Oh, that's way worse. Sorry.
Oh, like,
Yeah, you can try playing around with it. Oh, there. That's. Oh, perfect. Nice. Nicely done. In fact, I might be able to do this more. Okay. All right, cool. Yeah, so if there's no questions, I'm gonna finally start talking about the thing I promised, which is the FRI protocol. Well, not just yet. First, we're gonna go through a lot of like failed attempts at trying to make the FRI protocol. So let's say that you're given some function, which is like you know, maps some domain to some field elements, right? So equivalently, this is some vector of evaluations, blah, blah, exactly the thing that I said above. You can think about it as like a function or like a vector of evaluations. Okay, so we want a proximity test for this function to the Reed-Solomon code. And what we want is we want this proximity test to be complete. So if this function really is a code word, the tester should always accept. And it should be sound that if this function is like delta far from the code, then the tester accepts with like low probability, some epsilon that depends on this delta, how far away it was. You can think of delta here as being like a fraction between 0 and 1. And notably, like we want something that's better than like querying k plus 1 points, right? Like this is sort of what I said earlier, that like one way you could obviously do this is like, you know, it's a degree at most k minus 1 polynomial, so you can query k plus 1 points, use the first k points to interpolate a polynomial, and then see if the k plus first point actually lies on that polynomial or not. And that is a test, but that test is not actually great because in many contexts, including the context that we cared about and motivated, this like blow up from k to n is actually going to be like, you know, linear. k is going to be like something like n over 2 or n over 4 or n over 16. In which case, like, we don't want to be doing basically like so many queries. K is large. Okay. So what is like an IOP proof of proximity, whatever, for Reed-Solomon actually look like? Like, what is it structurally going to look like? You know, there's some instance, which is like this function that we want to test if it's low degree, and the verifier is going to send a message. The prover will send a proof string back, which the verifier can query at some places. Message proof string back, the verifier will query at some places, etc. Okay. So I'm going to make some assumptions that are like extremely important if you want to do the FRI exposition. The normal FRI was defined over like binary fields, or like characteristic 2 fields, let me say. To present it, I think that you must present this over like the prime field case. So we're going to assume that like the field, when I say f, it's like z mod qz for some prime q. Right? So the integer is mod q. And we're all more comfortable with that than some random Galois field. So our instance here is some function f, which maps some domain L of size like capital N to f. Another thing I'm assuming, sorry, is that like this capital N and this capital K here are both powers of 2. Okay. So our instance is like, we start with some function that is like a vector of evaluations. And like, what is the domain? Well, we can choose the domain as long as the size of the domain is like capital N, right? And what we're going to do actually is we're going to choose this domain. We're going to choose this domain to be like the multiplicative group generated by omega, where omega is some like order capital N element. Right. And,
You mean it's a FQ star?
yeah, sorry, you're absolutely right. Yeah, that's why I put this Toshin Q down here. Yes, so omega is some order N element in capital FQ star, which is the multiplicative group underneath the Z mod QZ. Okay, so that exists if and only if like N divides the order of FQ star, which is also known as quotient of Q. Blah. So as an example, we can think of this prime here. Yes, that's actually a prime. It's really cool. It's called the Goldilocks prime. 2 to the 64 minus 2 to the 32 plus 1. If you think about what like quotient of Q is, which is Q minus 1, that's 2 to the 64 minus 2 to the 32. Therefore, like 2 to the 32 actually divides Q minus 1. Right, so we can actually like do this FRI test for Reed-Solomon codes where the capital N is actually 2 to the 32, which is really cool. Okay, so like what is like the group generated by omega, the multiplicative subgroup generated by omega? It is exactly this, like 1 omega, omega squared, omega cubed, etc., all the way up to omega n minus 1. Because omega is of order n, that means omega to the n is the same thing as 1. Okay. Some slightly weird notation, which I believe is justified, is that I'm going to define like L squared to be the set of x squareds where x comes from L, right? And notably, you might notice that like L squared is equal to like 1 omega squared, omega to the 4th, blah, blah, blah. So what's going on here? Like basically like every element in L squared, right, came from specifically 2 elements in L. We'll see more of this later, but basically L squared is like half the size of L. And it's actually like the multiplicative subgroup generated by omega squared, which is order capital N over 2. Okay. So an observation that's going to be very important. Given like this P of x, which is like some polynomial of degree less than 2 to the k, I'm going to just call this k, capital K. Such that like f of x is actually equal to p of x. So let's say that like our instance f was actually a code word, right? that means that like there is some low degree polynomial that agrees with f at every single point in the domain. Then we can find polynomials, which I'll call like p even x and p odd x, that are polynomials of degree less than k over 2, such that the following is true. Right, I'm gonna let that sink in for a second. If p is of degree less than k, then there are polynomials p even and p odd that are of degree less than k over 2, such that this relation holds. Okay. Now, let's look at an example of that. Like, let's say p of x is like this giant polynomial here, and p even of x we can just define to basically be like, I did this. No, I did this correctly. Okay, it's just weird because I put like odd coefficients on the even term, whatever. Yeah, p even. Yeah, that's a bad example. I'm sorry. But p even of x is basically like the coefficient of x to the 0, the coefficient of x squared, the coefficient of x to the 4th. And p odd of x is like this guy, and this guy. And then if we square inside the x, we get this and this. And what you can actually notice is that like p even of x squared is equal to p of x plus p of minus x over 2. So what's going on here? Like maybe you remember like even functions and odd functions from calculus. Like if I do p of minus x, p of x plus p of minus x, like all these odd terms will cancel out. And then I'll get like 2 copies of each even coefficient, even term coefficient. And similarly here, if I do like p of x minus p of minus x, all these even terms will cancel out. And then I'll get like 2 copies of each odd coefficient, but like scaled down. So I need to like divide by x. Okay. I'm going to pause here and ask if there's any questions.
Maybe I have just a question to make sure I'm understanding what's going on. So we were looking at, I guess, like nth roots of unity, right? Right. Yeah, capital Nth roots of unity.
Yes.
And we were showing if you square all of them, they collapse in half to n over 2 roots of unity.
Yes. Yep.
And then also now we have this convenient representation for any polynomial where you break it up into even and odd exponents, and you're evaluating now at x squared. Am I understanding this? What's going on?
Yeah, this right now is like, I haven't really tied this into the broader protocol, but it's just an observation that like if we had a polynomial, we can break it up into its even coefficients and its odd coefficients in like this weird way.
But even and odd coefficients or exponents?
Even term coefficients. When I say an even term, I mean like a coefficient of x to an even power.
Yes. Okay, that's fine. Yeah.
Even term coefficients and odd term coefficients.
Okay.
And this equation will be true.
Okay.
Right?
Mm.
And like maybe you believe it intuitively, but like in case you didn't, you can sort of see what happens here. Right? And if you bump all these guys up by x, then you get like 2x, 4x cubed, 6x to the 5th. If you keep these guys as is, you get 1, 3x squared, 5x to the 4th. So this guy plus x times this guy is this guy. Right? Cool. Yeah, so that's actually going to be very helpful, as it turns out. There is like some more algebra stuff I'm hiding under the rug, but I think that this should suffice for now. So if you see that I'm like hiding something, you're probably right, but that's okay.
So if you have seen this FFT algorithm before, then this is very similar.
Yeah, this is like very much motivated by the FFT algorithm. It's this idea that like if we choose our domains carefully so that like there's a 2-to-1 map between my like initial domain. So basically what I'm like kind of doing is like the idea is kind of this, right? Like F was a vector of capital N evaluations. G and H are vectors of capital N over 2 evaluations, right? So instead of checking whether F is close to the code, maybe I want to check if like G and H are close to the code. Well, like actually a different code, right? Like a code where N goes to N over 2, K goes to K over 2.
Right. But then what do you do about the X in front of F odd? Because that's still in the original.
Yes, you're absolutely right. That's something that we need to be careful about.
Okay.
And that is something that we will have to deal with. But just the hope is that we could do something like this, where we can sort of reduce this subproblem to subproblems or a subproblem of half the size. And you're able to do this conveniently. Like I won't say right now, but I'll say later, like why it's nice that like L to L squared is like this 2-to-1 map. Yeah. Okay, more on that later. I don't want to overload you guys yet. Okay, but yeah, so specifically we've picked these domains, L, L squared, L to the fourth, etc., like very conveniently to be amenable to recursion. That's the intuition I'll leave for now. Yeah. And it's like very, very similar to why we've done it in, if you've seen those algorithms before. Okay. So yeah, so we had this like weird formula here. So let's talk about like how this recursion might look, right? Like we have this F which agrees with this low degree polynomial, right? And then we can make G and H agree with these low degree polynomials P even and P odd. Okay, we can like define them as such. Okay, and how do we compute like G of some value? Like, okay, so let me draw a picture. We have F like this, right? And we have G like this. So F is like some function that maps like L to F, and G is some function that maps like L squared to F. And remember, the size of L squared is half of the size of L. Like we want to compute like some value for G. How do we do that, right? You can say that like, oh, if there really is like a polynomial that underlies F, then you can like find the even and odd refinements of that polynomial, and then you can use that to figure out a polynomial that should agree with G, and then you can, that's like a very roundabout way. It would be nice if there was like, a formula that allowed you to compute G using like only a couple queries to F, and like you don't actually need to know what the like underlying polynomial to F is in order to compute like a specific point of G, right? Like it's nice if I can compute an evaluation of G without having to know what exactly like P even really is, right? And it's sort of this magic formula that I put down here, which kind of tells you how that's possible, right? If like P is a real polynomial, so P even is a real polynomial, and we have this like polynomial identity here, right? So if I wanted to try and define G in a way that it was consistent with P even over the entire domain L squared, then I can define G to basically like be some function that like cares about two specific points in F and combines them to make the evaluation of G. And now if I'm honest as a prover, like so there F really was a code word, there was a polynomial underneath F, then there really is a polynomial underneath E. If I do this kind of an operation. Okay. So yeah, so really like the crazy thing that's happening here is like I can get local evaluations of G using 2 evaluations of F. Local evaluations of H, which is like the claimed to be P odd, using 2 evaluations of F. And it's like not just any 2 evaluations of F. It's like specifically like the pre-images to the place I'm trying to evaluate G at. When you look at the map like x to x squared. I know this is a lot, so yeah. Pause again. Before I pause, let me just like explain what is like minus omega to the k. Maybe this will help give some intuition. So we can say that like, pretend like 1 up to omega to the 7th is my domain L. Then like 1 omega squared omega to the 4th omega to the 6th is like some domain L squared. So like if I map each of these guys to its square, you see something like this. Why does this go back to 1? It's because omega to the 8th is the same as 1. Right? So actually for each like guy here, if you like look at its fiber, or like you look at its pre-image, right? You see like there's 2 guys here that map to it. There's 2 guys in L that map to this guy in L squared. Right, this is another way to say like x squared is like a 2-to-1 map in Z mod P Z star.
It's just a collapsing or folding in half. Like the 2 things go to like
Yes, yeah, it's like a folding in half.
yeah.
If you've seen a fold, it's basically that.
It's sorry. Not like folding like recursion, but like I just didn't meant like collapsing literal like
Yeah,
like 8th roots of unity to 4th roots of unity.
exactly. That's what's going on here. Any questions so far? Okay. So now we can finally look at like the first attempt of a FRI protocol. All right. So I have some instance, which I'll say is like capital N, capital K, and then some function F, vector of evaluation. And then, if I'm an honest prover, I have a witness, which is like a polynomial, which actually corresponds to this F. And then a verifier has the instance too, right? Like the parameters to the code that we're testing proximity for, and then some function F that we want to test. Okay, so what the prover can do is it can compute G and H, right? Like so that G is the even refinements of P and H is the odd refinements of P. And it can send those functions over, again, as like vectors of evaluations. Okay. And what the verifier can do is it can basically check whether f of x is equal to g of x squared plus x times h of x squared. But like, how is it checking that? It's using like a polynomial identity test. Right? So like, is this g and h actually the related to f in the way that you're claiming? Like you wanna reduce f to g and h. So I as a verifier is like, is this reduction correct? So I check you. And there's a chance this check fails, but like it's a check to make sure that there's some semblance to you trying to convince me that you should be able to reduce this problem to g and h.
Wait, what is W? Sorry, is that omega or
This is
P of
yeah,
X?
sorry. This is like the witness. Like pretend like it's witness, not a witness.
But so we're trying to prove that F is close to this NK read some.
Yeah.
But so what is? Sorry, I think I missed it. What is P in this witness?
So P is like the actual low degree polynomial that corresponds with F. Like if the
It's
prover
code word, right?
it's like the message behind the code.
Oh, okay,
Yeah.
okay. Message window.
Right. So like if F is honest, there actually is a low degree polynomial P such that like f of x equals p of x for every x in the domain. Like, I can write that out.
Okay.
If prover honest, right, there exists like some p of x, which is low degree. That means degree less than k, such that for all like gamma and L, f of gamma equals p of gamma. Cool. Okay, so there's two problems with this attempt. The first one is that we have too many subproblems, right? Like right off the bat, if we take one thing into two things, and then 4 things, and then 8 things, and then 16 things, we're gonna have like pretty much D subproblems. That's not good. You know, we were trying to get away with doing like fewer than D queries. Why am I saying D? I should be saying K. Okay. The second problem, which is like a much more serious problem, is this one of distance decay, right? So suppose I started with this code word F, this word F, right? And recall that Reed-Solomon is a linear code, therefore 0 is a valid code word, all zeros. Now, these shaded regions are places where I have errors, right? Like the errors to my closest code word. And what's happening here is to compute this guy, I'm combining this guy and this guy. To compute this guy, I'm combining this guy and this guy. Similarly for H. But as a cheating adversary, I've defined my F in such a way that when you like do these combinations, you know, this error sort of like goes away. Despite the fact that I had like errors here and here, when you combine them to calculate what like G should be here, the error like disappears. And similarly, like I've made sure that if I combine this error and this error here, like it just disappears. So like what's happened is like my original function F had like a relative distance of like 1/4, like 4 out of 16 positions are corrupted. But my two subproblems have relative distance 1/8. 1 out of 8 positions are corrupted. So that's really bad because after R rounds, the distance can decay like exponentially in R, lambda delta over 2 to the R, right? That's very, very bad because generally like we want R to be about like theta of log K, right? So this is like a huge, huge decay that we cannot accept. Yeah. So is everyone clear like why this protocol does not work? Okay. Some head nods. Cool. So let's look at a second attempt. Our second attempt is do pretty much the same thing, except now the verifier is going to give us like some, I'll call it like a batching challenge, alpha, right? And instead of having 2 subproblems G and H, we'll like kind of batch G and H according to alpha to get like a single subproblem. And then we'll just send that single subproblem to the verifier. And then we recurse on like capital N over 2, capital K over 2, our new Reed-Solomon parameters, and subproblem. Okay. So basically the verifier is doing like 2 tests right now. Like, hey, like, are you really allowed to reduce F to G and H? Okay, this test passed, fine. Hey, is like this thing really the batch of the 2 things you gave me before? Okay, cool. So this actually does fix both problems, right? Like now we have only like log capital K subproblems only, and each are half the size, and it's also distance preserving with an asterisk. Like intuitively, if F had errors in all these places, right? Like maybe we did the thing earlier where we like, we were adversarial so that G only had errors here and not here. H only had error here and not here, despite, like coming from two error locations. The error was annihilated. When we take like a random linear combination of like G and H, right? Or like, I guess this is like an affine combination, but when we take like this combination of G and H, for most of these alphas that we choose, the error should like appear in both places. So that's great. So this protocol is actually like way better. We can actually simplify it a little bit. There was like no reason for the prover to send like G and H and then batch them. You can just like wait for an alpha and then batch what your G and H in your head was. And so I'll show that here. Before that, I need to now finally define like what folding is. So given a function f and some like folding challenge alpha, I can fold f according to alpha like so, which basically maps this generic element of L squared to this plus alpha times this. So what is that really like? What am I really doing? This is sort of to Julia's point earlier. This is just g of omega 2 to the k plus alpha times h of omega 2 to the k. Right, and when I write it out like this, without the g and the h, I'm sort of like inlining that whole, like instead of two steps, I'm just doing everything in one step. Like I'm not actually like computing g and h first. I'm like, just computing the fold altogether. So going back up to attempt 2, right? This right here is actually the fold of f with the folding challenge alpha. But like I didn't actually need to like do this intermediate stuff. Let's kill this. And that's what attempt 3 is.
Wait, so why is it not never using that these, like the verifier is doing a check there? Why can we eliminate that verifier's check?
Oh, great question. Basically, like the verifier is going to be like checking it all at once, essentially, right? Like if you see this check that the verifier actually ends up doing, it's sort of like doing both checks at once, that like both G and H were valid. Like if I replace, I sort of like, I'm trying to sweep this on the rug, but I probably shouldn't fully. Like what's going on is two things, right? Like earlier we had these two checks equals G of mu squared plus like alpha, mu of H of mu squared. And we had that like alpha of mu squared is really equal to like squared plus alpha H of mu squared. Right, we're sort of killing this one. Really like what's going on is like, I haven't presented it like this, but this decomposition from like F to G and H, you can sort of think about, instead of like being like a linear thing, is like you can think about it as like a bivariate polynomial in two variables, X and Y, with like some specific relation. And then this is like kind of like a more complicated form of identity testing, except for like bivariate polynomials rather than univariate polynomials. And like testing this actually suffices to check whether the fold happened correctly. There's like a little bit of algebra that I'm sort of sweeping under the rug, but hopefully like that gives a little bit more explanation. Like you can think about this as being like an X and this being like a Y or something. Anyways. Okay, so we end up like basically kind of inlining this and doing it all in one shot, never actually like sending G and H. and this is what the new protocol looks like. And we recurse on this new subproblem. F1 is now our subproblem. Okay, so there's like a small weird subtlety here. It's weird. I don't think I've even fully wrapped my head around this, but like I'll say it anyways. It's like the soundness error of this protocol, like, is going to be like at least r times the soundness error of like any round consistency check. So like this check here to see whether like F1 is really like a good subproblem for F has some like some soundness error. And if we keep doing it like this, where I send you alpha, you send me like F1, and then I check whether like what am I really trying to check here? I'm checking like, is F1 equal to like fold F with alpha? Let's call it like, let's call the initial instance F0, and let's call this guy alpha 0. So I'm checking that. Then like later I'm gonna check, is F2 really equal to like fold of F1 alpha 1 question mark, blah, blah, blah. And then each of these guys has like some error. It's not clear a priori why that error is actually like always the same, but like maybe you gain some intuition when you see that like the rate of this Reed-Solomon code is not changing. So like the best we can really hope for is like this like union bound result of like the soundness error being at least r times this error. And that's not good because like r is like log capital K, and we want to do better. Like we would ideally like the soundness error of our protocol to like not depend on K whatsoever.
Can you further explain the verifier check this? Because the prover just sends F1, and then the verifier is looking at the F alpha,
Oh,
G, and H.
shoot. That's my fault. That should just be F1.
It's F1.
Yeah.
Okay. And then where is it? Is it computing G and H? Wait.
Oh yeah. Okay. Lots of things happen. Like it
Sorry.
can compute G from yeah, no, I'm glad you unwrapped this. It can kind of compute G of mu squared from f of mu and f of minus mu.
Oh, right. Okay.
You can compute H similarly.
I guess this was
Yeah, this is what I was saying with
like the prelims, so like the decomposition of the polynomial. It says even and odd thing.
yeah, exactly. And then like if you want to abstract all that away, you just like you have this folding formula, which does this. And like where this formula came from was like the even and odd refinements. But like when you just look at this formula, you see that like, hey, I can calculate like this value just with like knowing the values of f of omega k and f of minus omega k.
Why are we chaining the folds?
Why are we what?
Chaining the folds
The
for each of the rounds.
chaining the rounds.
The folds, like
The
in the folds in
Oh.
the blue text you wrote.
Yeah. So what was I actually writing here? This is like the folding check that'll happen on F1 in the first like round. Then in the next round, like there'll be another like folding check that happens on F2. Right? Like is F2 actually the fold of like when we unwind this recursion, what happens? Like we get like these kinds of checks at every single round. Right? And then the point that I was trying to make, which probably is like unclear from my scribbles, is that like each one of these guys has the same error. Like none of these checks are like perfect. We're like kind of checking them at like one specific place. And so each one of these checks actually have the same error, which is not clear exactly why, but just believe me and we can call that error this. So if each one of these guys has the same error, then like the soundness error of our total protocol is going to be like something that unfortunately depends on how many rounds we have.
Oh, so I was just asking, like, why is for F2, why is it not just the code of F and alpha 1, or like a new alpha or a new challenge? Like, why do we need
Oh, I
to
see.
change the?
Like so F1 again is like of size half of F, right? And F2 is of size like a quarter of F,
Oh, okay.
right? So did that answer the question?
Yeah.
F2 will be the size half of
Yeah.
F1, right? So like each fold actually like decreases the domain by a factor of 2.
I have a question. So
Yeah.
whether soundness error is a bad thing. So
Yeah. You think it should be the other direction? What are you just saying that it should be a less?
yeah, isn't it already very small? So if it's the soundness error is R times some epsilon for some single round check. So the number of rounds is log.
Yeah. So I think that if I'm not mistaken, in the end you'll get something that doesn't depend on the rounds. So we can do it better. There's like another answer that's like also. Okay, so I'm gonna go on a slight tangent. I'm sorry. Basically, FRI is like this information theoretic thing, right? But when you actually compile FRI into a real protocol, you use like an IOP plus like some commitment scheme, and you can't just query the oracle. Like the verifier has to tell you where it's querying. So if I query, like if I tell you where I query on F1 before you submit to me like F2, then like actually, sorry, I'm gonna just like completely kill that thread. It's gonna be more obvious when I explain something later.
Can't you just send all? Why can't you just send all of the alphas first? If you're compiling it with a commitment sort of thing, like are all the alphas just independent?
You don't want to send like everything first because it gives the prover like an easier way.
Oh, I see.
Right? That's kind of the point I'm making.
I see.
Yeah.
Okay. So you want to you do for soundness, you want to do some sort of interleaving of send alpha and do a check and send alpha and do a check. I see. Okay.
Exactly. Since I just told you that, I'm going to say the complete opposite now, which is that actually what you want to do for soundness is you want to send alpha, and you keep sending alpha, and you get like a new oracle. Send alpha, get like a new oracle of or a new function of smaller domain, and you keep doing that, and then at the end you can actually do all of your consistency checks, all at once, right? And maybe there's a couple of things. Like I said, this is a really subtle thing. One is that it actually makes the soundness error of the protocol better somehow. But two, it's it's absolutely necessary if you're doing this in the real world, because you don't want to do your consistency checks until the prover is committed to all of the oracles, because then the consistency check that you did. Yeah, this is really crazy. So maybe you guys will also take away some intuition from how this proof actually works. But all I will say is right now it is not very obvious, to me at least, why doing these consistency checks at the end in sort of what I'll call a correlated way is actually better. We'll see it in the soundness analysis a little bit. Okay. So our new protocol, this is our final protocol. This is the FRI protocol now. Is that the verifier can sample all of these guys ahead of time, sure, but it only sends it to the prover one at a time, alpha 0, then fold alpha 1, then fold alpha r minus 1, then fold. Okay, and then once I've gotten all of the F0, F1, F2, etc., then I do these consistency checks, and I do it in this kind of correlated way. So I start with some mu in my original domain. And then I check whether F1 on mu squared is actually equal to fold of F0 alpha 0 on mu squared. And how do I compute this fold again? Well, I need to know the values of F0 mu and F0 minus mu. Right. So the query access pattern that's actually happening is like I'm looking at these guys on F0. I'm looking at these guys on F1. I'm looking at these guys on F2, etc. These guys help me fold at F0 to F1. These guys help me fold at F1, etc. Yeah, is that clear? Or is this confusing to people? I'll leave the protocol up for a second so you guys can read it.
I see. So you use the same U to check all of the.
Yes, I'm using the same mu, so it's like it's correlated actually.
Is this, yeah, I think I'm wondering what the same mu that's.
So
Yeah, why is it the same mu?
yeah, that's like the $1 billion question. It's a fantastic question. Like, first of all, it's okay for me to use the same mu because like the prover's already given me all of the oracles, so it can't cheat knowing that like I'm reusing mu.
Yeah.
That's a good thing. The second thing is that like, as we'll see in the soundness analysis, like this helps you like. This helps with one of the steps of the soundness analysis. The fact that I'm using the same mu.
Okay, so it helps boost soundness, but it's also okay to not use this. You just get worse soundness.
Yeah. I mean,
but you don't have to use the same. I think I'm just wondering like
mathematically, it seems to be better. That's what I'm trying to say.
No, like the correctness. Sorry, completeness would still hold if you use different mu.
Oh yes, 100%. Yeah, like these consistency checks will pass no matter what mu you choose.
Okay.
If
But
it's
really-
Ruber's honest, yeah.
Okay, it's really for sound.
This is all for sound. Everyone good?
So the fundamental intuition is just that like choosing using the same mu throughout can't possibly hurt soundness because you've already committed, you're already stuck. Like you all your choices have already been made. I'm
Yes.
doing this check at the very end.
Yeah.
So okay. And then you're saying that it's actually going to help us. And you haven't showed us that.
Yeah, exactly. So it seems.
Okay.
Yeah. Yeah, like okay, usually if you do this protocol and you make R equal to like log capital K, then FR will be like, it should be like all constant, like all the evaluations are constant. It should correspond to some constant polynomial. Hypothetically, you can like end early and then like send a vector of evaluations and say, hey, now it's up to you to check whether this thing is really like degree less than 10.
Okay.
But the simple version of the protocol is like I send you a constant.
Yeah, go all the way down to the bottom.
All the way down to the bottom.
Okay.
Okay. All right, so that's our FRI protocol. Now we're going to talk about some of the intuition behind soundness. So first, we're going to lower bound the soundness error. I'll start by like, letting the cat out of the bag about something. Like we don't have tight soundness error known for this FRI protocol. We don't actually know like what the best soundness error is. And like, what is a lower bound? What is an upper bound? A lower bound, like I show you an attack that actually like succeeds with some like probability, and an upper bound is like I give you like a proof that no attack can succeed with more than this probability. And there is a gap between that lower bound and upper bound, and it's like a major open problem. And it really matters in real life too what the soundness actually is. Does anyone have like a Mac charger I could borrow?
You see upstairs.
Oh. I'll make it work. It's longer than mine. So
I have a long one, so-
that's okay. I think this should be fine. Computer is really only being used to like see my face because I'm sure people want that. Cool. Okay, so yeah, so let's lower bound this soundness error. So let's show a simple attack. Right? And our claim is that there exists a cheating prover that makes a verifier accept some delta var word f with probability at least this. So what is this like term? This is like something that's dependent on our field size, which really suggests that if you want to like use FRI in practice, you need like a cryptographically large field. Okay. And then the second thing is like this, 1 minus delta to the t, which is sort of like, 1 minus delta is like sort of your chance of even being able to see whether an error happened. Now, 1 minus delta fraction of stuff is like okay, right? Because we're delta far away from the code means like 1 minus delta is actually close to the code as a fraction. Okay, so let's consider a simpler case where like, delta is less than 1 minus rho over 2. This is sometimes called a unique decoding radius. What is rho? Rho is the rate of the Reed-Solomon code. Anyways, all you really need to know is that like if delta is less than 1 minus rho over 2, then that means that there's like a unique code word that I'm closest to.
So what is T?
What is what? T? Oh, T is the number of, so yeah, I didn't emphasize this, but like we can boost this consistency check, right, T times.
I see.
Okay. That's the number of like different mu's that we sample and then run the whole query phase on. Okay, so the way this works is that we will partition L into two sets, S0 and S1, such that the size of L0 is like 1 minus delta the size of L, and the size of L1 is delta times the size of L. Actually, what we'll want is we'll want like inside of these sets for squares to be preserved. So like if mu isn't, oh my god, what's going on? Sorry. If mu is in like one of these sets, then mu squared should also be in that set. That's a very important condition. Now, we can consider like F0 to be like our delta var word that we're going to cheat with. And we define it like this. We put zeros everywhere in S0, and we put like some line Q on S1. And Q must satisfy the fact that it is not 0 anywhere in S1. Why do we care about that? Like we're trying to say that this thing is delta far away from a code word, right? So the closest code word here, because we're in the unique decoding radius, is going to be like the zeros code word. And then all these guys have to be not 0 for me to say that this guy is like delta far away. Okay, so if we put like a line here, then I can, and I'll choose my other oracles to just be like F1 equals F2 equals FR equals 0. Now, the chance that I have like a consistency check, oh my god, my pen is like, sorry for all the technical difficulties today. Yeah, so the chance that all my like consistency checks fail is like equal to the chance that like my first consistency check fails from F0 to F1. Like if the verifier does not catch me when I reduce this problem to F1, then the verifier is not going to catch me, right? Because after that, I'm honest. So what is the chance that my first consistency check fails? Well, it's like 1 minus delta to the t. Right? This is assuming like no distortion. Well, I'll define what that means later. But it's at least like, let's call this at least 1 minus delta to the t. Right? And then what is like this distortion? Well, this is like this weird scenario where like when I fold F1, F0 and get F1 with this folding challenge alpha 0, like it actually turns out that the folding of F0 with this unfortunate folding challenge turns me into the all zeros polynomial. Like this is some like maniacal case where like all of a sudden I folded this guy with like your folding challenge, and now the actual result of that fold is like the all zeros code word. And this happens with probability of 1 over the size of the field. Like there's one folding challenge where this will happen in the entire field. And that's specifically where like alpha 0 is a root of Q, this line that we drew. And so I have like put like a mini fun homework problem I came up with down here, which illustrates this attack. Basically, we can take like our field to be like Z mod 17Z, and then we can think about like our domain as being like the multiplicative subgroup generated by 2. And this domain is actually of size 8. And what I'll say is that like if you like split this up into an S0 and S1, where S1 is like generated by 4 and S0 is everything else, and then you consider like a line like this, and you define your F0 like so, right? Then you should be able to prove that like the fold of this F at some alpha is equal to 0 if and only if alpha is a root of this polynomial, this line that you chose, Q. I won't go into detail about this too much because it's like there in the notes if you want to try it. This could be helpful if you like want to build up your intuition on how this simple attack works. And I provided like explicit parameters to hopefully guide you through how to check this for yourself. Okay, but the idea is like is really this, that like I drew a line over S1, and then like if my folding challenge happens to be a root of that line, then like F0 folded with that folding challenge gives me F1, which is 0. And then as a verifier, I'm screwed. Okay.
I'm trying to think like does this, okay, maybe I just have to think more. I'm just trying to understand if this means anything about I guess it doesn't make sense. I don't know. Like if F even and F odd are scalar multiples of each other, you just have to be true. The negation of but is it all? But what am I missing?
I see what you're thinking about. I'll show you what you're thinking about. Okay, I don't know if I can do this without like way too much algebra.
Oh yeah, that's
But
I just I don't even know if I.
This is sort of what you were thinking about, right? Like I want, if I make G0 and like H0, or if I make like G plus alpha H equal to 0, then like I won the folding game with alpha.
Well, like they have to be G and H have to be multiples of each other. Like the way that the coefficients line up, and then you have to choose the alpha,
It's
the negation of that, so that
slightly
they.
more complicated than that because of this term here.
Oh, okay.
Right.
But
But I see like your intuition is correct about how to try and.
okay, yeah, I forgot about the denominator. Okay.
But yeah, if you really want to try and like get more intuition about this, I encourage you to try this exercise. Okay, cool. Any other questions about this like lower bound for soundness? Like basically I've said that like either the prover wins with like this probability or this probability. Or like just union bound these guys, I guess. Okay. Now we get into the real meat of FRI, which is like actually trying to prove like a soundness error bound. And there's two cases that we'll talk about. There's like an easy case and a harder case. And I really want to like focus on trying to give the intuition for the easier case. And if we have time, like we can maybe talk about the harder case. But in the easier case, we're going to make a lot of assumptions. The first assumption is that like our prover is consistent but noisy. And the second assumption is that like all functions FI are like close to the code. But, like we're actually going to define like a new version of close, which may appear unmotivated at first, but as you unwrap things, you'll see why we need it. So yeah. So we're going to define this like new like closeness thing called blockwise distance. And again, like it should be clear that like this is relative distance. And blockwise distance is like all of the gamma squared such that like either f of gamma is not equal to g of gamma or f of minus gamma is not equal to g of minus gamma, right? It's like all of the things like in, so f is from L to f, right? When like I actually turn this into something from L squared to f, right? Like basically like, did I have an error in any of like my pre-images in the 2-to-1 map is one way to think about it. So this like blockwise distance. Remember like normal distance is just like component wise. Like I don't count gammas and I don't count gamma squares and L squareds. I count gammas and L. And then I just ask like, is F and G disagree at that point in L? Okay. So this is blockwise distance, right? Like specifically like this thing is a subset of L squared, and then the denominator we divide by L squared. And then a normal distance, like this thing is a subset of L, and then we divide by L. Okay, now I have a claim, which is that like the blockwise distance is always at least the normal distance. And the reason is because this is like all the blocks are the same size. Like maybe as I'm saying this, I realize maybe it's time for a picture. Yeah, let's really zoom in. So let's say that I have this guy here, and then okay, this is not cooperating.
Is it from your wrist touching the screen?
Yeah, it might be that actually.
Oh, that's so weird.
Okay, so let's say that, okay, I'm gonna give up on this. I'll try and
The whiteboard?
Sure, I could. No, I'll try one more time here. I'm just gonna make a new page. That way I don't need to like zoom into oblivion. Okay, so I'm showing that blockwise distance between like f and 0 is always greater than or equal to the normal distance between f and 0. Okay, and why is this true? Okay, let's look at an example where it like might not be true. Like suppose I had these two blocks. I'm really sorry, guys. So suppose I had these two blocks, right? And now let's suppose that like everywhere I shade is an error. Okay. Now, what is the blockwise like relative distance? So like delta of f0 here would be equal to like 1/2. Like one of my two blocks was corrupted. Right, like This guy is like defined to be corrupted if any of the things inside of it are shaded. So like this guy is a corrupted block and this guy is like a fine block. So there's 2 blocks in total. 1 out of 2 are corrupted in this example. But like what is my, I have no idea what's going on with my iPad. Okay. My normal distance, I'll try and just like talk, I suppose. My normal distance is like, I count the number of cells that are corrupted divided by the total number of cells. And as you can see, like the total number of cells that are corrupted is like way more than 1/2. Since like my pen's not cooperating, I'll just say this part. If I had changed this so that all the blocks were the same size, now it's the case that like my number of corrupted blocks over total blocks is always at least my number of corrupted cells over total cells. And what is a block in the context that we care about? A block is like the 2 pre-images of L in the specific point I cared about in L squared. So each of these blocks are like size 2 blocks. Cool, yeah. And similarly, like, yeah, we can define like, you know, normal relative distance to the code and like blockwise relative distance to the code as exactly how you'd expect. Okay, so that was some definition. Oh boy. so some more definitions. Drop f of delta is going to be the set of bad alphas, bad folding challenges, such that like when I fold f on alpha, then my result is actually smaller than delta in distance. So let's actually look at this guy first. Something very subtle is going to happen here, and I want to like really belabor the point. So we can define delta I to be the blockwise distance between Fi and the ith Reed-Solomon code. Okay? And now what I'm saying is like if I pass in, if I think about what drop of Fi delta I is, it's going to be the set of bad alphas such that when I fold Fi, then my normal distance, normal relative distance is less than delta. So like, maybe I should write this out if I can. So delta I can, okay, hold on. Let's try this. So here, delta I is my blockwise distance between, okay, I'm gonna just try using words. Delta I is my blockwise distance between Fi and my code. Drop f of delta I tells me like how many alphas will make the folding thing's regular distance be less than delta I. And so we're relating like the blockwise distance of Fi to the normal distance of fold of Fi. Is that clear? Okay. And we can similarly like define like f twiddle of I to be like the closest code word to Fi. So again, what is Fi here? Like this, there is some run of the protocol. Right? There were some Fs that were used. Fi's are those Fs. Delta I's are like the values for those Fs in terms of blockwise distance to the code. F twiddle of I's are like the actual closest code word to those Fi's. Finally, two more sets that I care about. Error of I is going to be all of the A's and Li such that like there is either an error at FIA or an error at FI minus A. And then fail of I is going to be all of the A's and Li such that like Fi at that A is not equal to my previous guy folded at that A. In other words, fail I is like all of this places that a verifier could test consistency between Fi and Fi minus 1 and catch you. I saw that you cheated when you tried to submit Oracle Fi. And like, it's all the places the verifier could look and see that like, hey, Fi was actually not consistent with Fi minus 1 and the way it was supposed to be. Okay. Any questions right now?
Yeah.
Yeah.
So what is capital C?
Capital C is my Reed-Solomon code, sorry.
I see. So it's the Reed-Solomon code with that parameter on the
Yeah,
FI line.
Yeah, this n over 2 to the I, k over 2 to the I. Yeah. Thanks, yeah. Any other questions about these definitions? So before we move forward, I want to make sure that everybody is like comfortable with like what blockwise distance means versus like normal distance. And then I want everybody to be comfortable with like this idea of like this drop set, right? It's like all the alphas that somehow like when you fold it, you get worse distance than you had before. Okay. And then like the error set is like all of the places where like either me or like my like neighbor, I'll call it, are wrong. Like either FIA is wrong or FI minus A is wrong. And then the fail set is all the places where the verifier can check you for consistency and see that you lied. Okay. So back to the supposed easy case. We're going to assume three things for simplicity. We're going to assume that we always are within unique decoding, right? We're going to assume that the unique corrections are always consistent. So that means like if I fold the closest code word to Fi, then like I get like the closest code word to Fi plus 1. And finally, we're going to assume that we never choose like a bad folding constant, folding challenge alpha I. Right, so the distance is like not decaying. There's no distortion. Remember the bad example I had earlier where like F had like 40% errors and like G and H both had 20% errors. And then I said G plus alpha H might have like 20% error if you get really unlucky with that alpha. Saying that we did not get unlucky with that alpha. We're just going to assume that. Okay. The lemma that we can prove is that the probability that we reject is basically the size of the error of 0 over the domain size L, which is the exact same thing as delta 0, which is like how far away our initial word was from the code. Slight asterisk, again, this is not like actual farness. This is a blockwise farness. But that doesn't really matter. As you can probably see, like blockwise farness is always greater than like normal farness, but like it's always less than 2 times normal farness because our block size was 2. So basically, we're gonna somehow like in this easy case say that our probability of rejecting is at least like I can write it, say like deltas. Oh my god, why is it dying on me? F0 to RS and K over 2. Is everyone clear what we're going to try proving? Okay, so here's our proof idea, and now I finally will answer like Ethan's question and come to the intuition of why like using this correlated query checking is actually useful. So basically, like here's the proof idea. Like, if I sample some mu0 in the domain, that uniquely determines like mu1, mu2, mu r, because the mu I plus 1 is just mu I squared. The final oracle you send me better have no errors, because like the verifier is going to like straight up check that that's a low degree polynomial. Okay, so that means that there exists some j less than r such that mu j is in the error set and mu j plus 1 is not in the error set, right? Because we started with a mu that was like, okay, I also forgot to say, like, suppose suppose mu0 is in error 0. It's like an important. Yeah. So if mu0 is in error 0 and mu like r is clearly not in error r, there's some point where like we switch from being like in the error set to not in the error set, right? So there's some j where like mu j is in error j and mu j plus 1 is not in error j plus 1. Okay. That means that, okay, without loss of generality, we can also always assume, because it's a linear code, that like all of the like corrections, like, the closest code word is always the all zeros. The reason you can assume that is because if it's not, you can always like scale it down, because like the difference of code words is still a code word in linear code. So without loss of generality, we're assuming that like the closest code word is always 0. And now what we have is that f of j plus 1 mu j plus 1 is somehow equal to the correction of at mu j plus 1, which is equal to 0 by assumption, or without loss of generality assumption. And the reason these guys are equal is because mu j plus 1 is not an error j plus 1. Right? That means that like these guys are equal. It's equal to its correction at mu j plus 1 by definition. But, and here's like a claim that requires proof, if I fold like fj at alpha j with mu j plus 1, then I should not get the same thing as if I folded like 0 at alpha j with mu j plus 1. Basically, like this folding should not give me 0 at the mu j plus 1 position. This requires proof. So I'm saying that like fold of fj alpha j at mu j plus 1 is not equal to 0, but fj plus 1 at mu j plus 1 is equal to 0. Another thing that means is like mu j plus 1 is in the fail set of j plus 1. Well, being in the fail set means that like the verifier caught you.
The step with the star where the foldings are not equal.
Yeah, that's like a there's a proof behind that.
Sure. Is this except with, is there like probability like 1 over field size or?
Great question. So we've assumed a lot of convenient things. We've assumed that like alpha is not in the drop set, which is basically like that probability that you're referring
Oh, we already
to.
used, okay.
We've also assumed that like everything's decoding radius, and we've also assumed that like the corrections are consistent. Like, what do I mean by correction? Like, let me try and give you more intuition about like what a cheating prover could do. One, it could just send a bunch of noise. Two, it can send like a function like here that's like close to this code word, and then the next round like, hey, it's close to a different code word, blah blah blah. Like what we're doing in this easy case is we're really like saying, let's only consider the scope of cheating provers that do these things, right? Like we're always within unique decoding, like we're always like close to the same code word, etc.
Mm-hmm.
Okay, so yeah, so basically like to answer the question earlier, like the reason that we like this correlated query checking is because it guarantees us that we're eventually going to like land in the fail set. If we started in the error set, we will eventually land in the fail set. That is the crux of the easy case that I wanted to teach. Yeah, I guess I'm like running out of time. So I'll just like mention a bunch of further work that I find interesting. So there's obviously like a polynomial commitment scheme that for univariate polynomials that's based on FRI, and it uses the same KZG trick that we saw yesterday. There's another thing called like basefold, which like creates like a multilinear polynomial commitment scheme based on FRI, and this makes a really cool observation, which is that like if you fold with like these coefficients like alpha 0 all the way to alpha r minus 1, what you get in the end, like what is the like, so we're doing some folding on like the functions, but like we should remember like stuff is actually happening to the underlying polynomials that these guys are close to, right? And if we look at the final polynomial, what you actually get is that final polynomial's value is really the evaluation of some like the constant at the end is really the evaluation of some multilinear polynomial at the folding challenges. And now you can make like a polynomial commitment scheme based on that. The question you might have is like, okay, but I want to open to a specific point, not to a random point. Well, you can actually use like sum check, like kind of in line with the folding in a cool way, which allows you to like relate the evaluation at a random point to the evaluation at like a specific point of your choosing, using like this EQ indicator trick if you've seen it before. There's another work called FRI-Binius, which like makes multilinear polynomial commit schemes over towers of binary fields. And this was my previous job, so I put a smiley face next to it. Like I was working on Binius and FRI-Binius like stuff. It was very fun. Basically it combines like basefold with like the original type of FRI, which was over binary fields. And yeah, like it turns out like a non-trivial number of things have to change. Finally, there's two more things. There's this work called STIR by like Chiesa and Giacomo and some other great people. And the idea here is that like at subsequent rounds, the prover is like really doing very little work, but the verifier is still doing like a lot of work. You know, if you actually change it from being like the size of the domain is n to n over 2 to n over 4, and like maybe you decrease the domain like a little bit slower, so like future code words have more redundancy, then the verifier has an easier time trying to do its consistency check, right? Because more redundancy means that like the verifier needs to boost fewer times than t, the number of queries, in order to try and catch the prover with some good chance. That's a code switching technique if you've seen something like that before. And then finally, like there's this thing called like distortion. Like we talked about distortion a lot. Like what's the probability that like when I batch these FRI instances, my new FRI instance is like, you know, still equally far. This is a very interesting thing. You know, my colleague at Olvatana, like Irreducible, this Binius company, gave like a 1.5 hour long talk about this on YouTube. You could look it up. It's really fascinating. There's like a huge line of work in this. An extreme simplification about what this like proximity gap is talking about is like, hey, if I take like a random linear combination of words, if that's far from the code, then with high probability, all of those words were far from the code. So it's like a good check. It's like an extreme simplification, but basically it like gives us a way to like batch like proximity testing. If a random linear combination is far, then like with high probability everything was far. And this is sort of related to that drop set that we were talking about before. Unfortunately, we ran out of time. I was not able to like talk about like the harder cases of FRI, or even really finish the easy case for soundness. But hopefully this is like a good start, and like I'm happy to answer any questions offline or whatever. Just feel free to ping me. I love to talk about this stuff. Thanks everyone for listening.
Yeah, thanks.
That's it for me.
Thank you.